Okay, let's discuss conductors in static equilibrium. So a conductor is a material that has free electrons, and any material with free electrons, when it's in static equilibrium, will have these 5 properties. So I'm going to list the properties, and then I'll discuss each of them in turn, illustrating them with examples. So inside a conductor, the electric field has to be 0. That implies that if we put any net charge inside a conductor, it's going to all go to the surface. So the net charge inside a conductor has to be 0 if the field is 0. And that means that any excess charge put on a conductor always resides on the surface. It doesn't mean that there's no charge inside, but that the net charge inside is 0. The electric field at the surface, where the excess charge is, will always leave the surface perpendicular to the surface. And if a conductor has a shape which is not spherical, then charges will tend to cluster and the field will be stronger where the surface is more curved. That means that strong fields will be found at sharp points, and weaker fields will be found where the surface is almost flat. Okay, let me see if I can, let me reduce this, put it here. Okay, so let me explain what you're looking at. Here are the 5 properties of conductors in static equilibrium. Here's an area of uniform electric field. Here's a solid conducting sphere. And here are 4 charges. So notice what happens if I put a charge inside the conductor. Then that's going to lead to a field inside the conductor, right? Picture the field. So now we have something that's forbidden. We have a charge inside a conductor. We have an electric field inside a conductor. And why doesn't this work? Well, because there's a field here, and a conductor has free electrons. So one of those free electrons is going to move and cancel out that charge, and that leaves a positive charge somewhere else. So basically, as an electron moves, now another electron comes, and electrons are going to keep moving inside the conductor until the excess charge gets to the surface. And once it's at the surface, it can't move any further because it can't go off the surface. It's free to move inside the conductor, but once it's at the surface, it's going to be fixed in place. And so if I put a bunch of charges in there, the same process is going to happen. And naturally, since they repel each other, they're going to distribute themselves over the surface. So now we're back to our equilibrium condition. We have no field inside, there's no net charge inside, and all the excess charge is on the surface. And according to this rule, the field lines, I'm not going to draw them, but the field lines would leave like that, perpendicular to the surface from all the charges. Okay, now let's try something different. Let me remove these excess charges and take our conducting sphere and put it into a field. So when I put it in the field lines go through, and so we violated this equilibrium conditions. So what happens? So now there's a field inside. So picture this, the field. So there are free electrons in here. And free electrons move opposite the field. So a free electron is going to move over here and terminate this field line. So what we would have is a negative charge here. Let me pause. Okay, now I got some negative charges to work with. So one of the free electrons in here is going to move to the edge and cancel that line. Well, of course, that leaves a net positive charge. So that positive charge will drift over here, or electrons move until we have this arrangement. So now notice, this line is gone. And one by one, right, one by one, we can move charges over to these lines, terminate these lines. And so what we still have a short one pair of charges to cancel that fifth line, but you get the idea. And so the conductor is still net zero charge, but the lines coming in terminate and don't go through, and the line then emerges from the other surface. And so what I've done is I haven't changed the overall field, but except for this line, the field inside the conductor is no longer there. So the charge is rearranged to prevent that from happening, and now the conductor is in static equilibrium again. Whoops. Let me see if I can fix this. Yep. Let's put this out of the way. Bring this new figure back. And so we're here to illustrate this fifth property, that the electric field and the charge density is stronger where the curvature is greater. So where there's very little curvature, you see the charges are pretty spread out. Here there's very little curvature, the charges are spread out. Here there's a moderate amount of curvature, and so the charge density is fairly moderate. Here there's a little more curvature, so they're more tightly packed. And here is a place of high curvature, and so they're very densely packed. So another way of saying this is charges tend to accumulate at sharp points on a conducting surface, which is irregular. So this is a good figure to illustrate that property. I'm going to put this away, and then we're going to do, I can rotate this, then we're going to do some problems related to those in the homework. So here's a problem you'll see among the homework problems. Let me show you what you're looking at. You're looking at an inner conducting sphere that's solid. You're looking at a shell, or kind of a ring, but a three-dimensional shell, which has this much thickness of conducting material. And they're all centered on each other. And I'm going to take a charge of +8 and put it here. And I'm not going to put any charge on the outside. The I is for the inside sphere, and the O is for the outside ring. So if you know what to do, I think you know what to do, try that. If not, you can pause the video. If not, you can continue to watch. So I'm going to put the 8 charges here, and I know from our conductors in static equilibrium that they're going to distribute themselves evenly across the surface. And I know that the field lines will go from the surface perpendicular to the surface and go across, but they can't go into the conductor. So they're going to go from one surface to the other surface, because I know in static equilibrium a field line can't penetrate the conductor. So it looks like that. But in order for a field line to terminate at the surface, if the field line went through, an electron, free electron inside the conductor would move here. And so in order for those to terminate, we have to have a -8 charges. I'm going to put them a little bit inside so you can see them, but they're really on the surface. 8 negative charges would come here, because they're free to move, and that eliminates the field inside the conductor. And so I have 8 positive charges here, 8 negative charges here, but the conductor is neutral. So when an electron comes in, that leaves a positive charge. And by our rules of static equilibrium, those positive charges have to end up on the surface of the conductor. And so if we're outside this shell and solid sphere, we see 8 field lines going away, same as on the inside sphere. And if you think about Gauss's law, the amount of flux, 8 field lines, indicates the presence of positive 8 charge inside. So we have positive 8, negative 8, which is 0, positive 8. So inside, we might not know how it's arranged, but we have a net charge of positive 8. All right, let's try another example. Okay, let's do one last example. Let's change the inside charge to a negative 12. And let's put a charge on the outside of positive 8. Okay, now given that, see if you can do it. Pause the video and see if you can arrange that charge. So start with the center, put the negative 12 there, and you know by the rules that they all have to go to the surface because there can't be any field inside. So we have 12 charges on the surface. So what does that mean? That means that those field lines coming in have to come in from the surface. So what you have to have is you have to have a positive charge here. You have to bring 12 positive charges. I'm going to pause the video. You're going to have 12 positive charges coming in to the inner surface so that there's no field inside this conductor. Because imagine if a field went through, a positive charge or a negative charge is going to move to that. Positive charge is going to end up on that surface. So I'm not going to draw all these lines because it kind of covers up the charges, but on this surface there should be 12 positive charges. On this surface there should be 12 negatives. The 12 negatives are here because we're given 12. The 12 positives are here because 12 positive charges must come in to provide the charge for the field lines that can't be coming through the conductor. So if I draw this out, there's going to be, I ended up drawing it, 12 field lines, 12 charges on each surface, and 12 field lines in this empty space between the conductors. Notice there's no field here, and there's no field here. But Q outside has a charge of 8, and we brought in 12. So what does that mean? Well, the excess 8 came in, and we needed another 8, so that leaves, that leaves 4 negative charges evenly distributed around the surface, and 4 field lines coming in like this. So if we look at the outside conductor, if we look at the outside conductor, we see that there are 12 positive charges here, 4 negative charges here. If we add all that together, we get our net charge of 8, which is what we put on there. And if we take the entire charge inside the conductor, negative 12 and negative 8, we're left with 4. So remember Gauss's law. If we drew a Gaussian surface around this, then the flux would have to be equal to the charge inside, and the charge inside would be a -4, and that's what we're seeing. We're seeing a field and a flux as if there were a -4 charge located at the center of the sphere. So that's how you do those problems, and we're done.